Math and Beats. Here's a video in which we are going to talk about a theorem which is called the extreme value theorem. Let's get going. All right. So the goal of this, at least initially, is that we'd like to establish a relationship between a function's global extrema and the corresponding function's behavior. How does this all work out? That's our goal. So we're going to take a look at this. We're going to try to figure this out by considering some graphs of some functions we're about to look at here. So we're going to look at 4 graphs, and this is going to hopefully allow us to conclude something about global extrema in relationship to a function's behavior. All right, here's the first function. Okay, right here, what do we got? Got a function right up here, f of x, let's call it negative quantity x minus 1.5 squared plus a 2. Now, on this example, we're going to restrict for which this function is defined to be values of x over this closed interval here, 0.25 to 2.5. Now we can see the graph given to us right here, right? It's just that part of the parabola where we've restricted the domain. And it is what it is, right? There's our beautiful looking graph. Now, the goal is to figure out what's going on with the global extrema. Now, in this case, we can see a couple things just from the graph. Right away, we can see that the global max is going to occur at the vertex of this parabola. So where is that? Right there. There's my global max, right? Global max, or absolute max, occurs at this value. X is 1.5. And what is it? Well, it's at the point 1.5, comma, 2, right? So global max value in this case is going to be equal to 2, and it occurs at the location of x is equal to 1.5. We can also see at the endpoint right down here, the left-hand endpoint, that over this particular interval, that's the smallest the function gets. So right there, there's our global min, and it occurs at the location, well, x is 0.25 there, right? That's our left-hand side of our interval. And if you were to plug that 0.25 into the function and evaluate, you would get 0.4375. So in fact, the minimum value, global min value here, is equal to 0.4375. One thing to take note of, one of the global extrema occurs at an endpoint. The other global extrema occurs at, actually, a local extreme point. And moreover, notice right up here at our global max value, f prime of 1.5 is equal to 0 there, right? The slope is 0. And in fact, that location 1.5 comma 2 is also a critical point. So we're going to look at some more, but something to get started here. We have a function. It's behaving quite nicely on this interval, right? In particular, it's nice and continuous. And the interval is a closed interval, and the function obtained both its global maximum and its global minimum values. So that happened. But we're going to look at a couple more here to try to get a better grasp. All right, here's another function. G of x is time 4 to the negative x power, and this time we're restricting the interval of x values to be on the closed interval 0 to 2. We can see the graph given to us right here. One thing to take note of right away, this function does not have any local extrema on this interval. In fact, this function is strictly a decreasing function. It doesn't have any local extrema. However, it does have global extrema, specifically over this interval. We can see that at the right-hand endpoint, at x is 2, there is our global or absolute min value there. And what's that going to be? Well, it's going to be the value of this function when x is equal to 2. So that's going to be a 1 over 16, right? 4 to the negative 2 power. That's occurring at the ordered pair, right? 2, comma 1/16. Its global max over here on the far left, since it's a strictly decreasing function over this interval, is going to occur, well, let's write that down, global max at the location, well, that's when x is 0, the output there is 1, and the global max value for us is equal to 1. So in this situation, again, we have a nice continuous function over a closed interval, and indeed, it obtained its global max and min values. In this situation, they were both at the endpoints. Unlike the first graph we looked at, this function does not have any local extrema, but it still obtained its global extrema over the closed interval. A couple more here before we start wrapping up what the conclusion should be. All right, here's kind of a more involved function. Here is a polynomial function, this cubic function h of x right up here. X cubed minus 4.5x squared plus 5.75x minus 0.875. So a lot of decimals, but it is what it is. There is the graph of this function over the interval of x values, 0.25 to 2.4. We can notice several things occurring here. This function, again, is a nice continuous function over a closed interval. And in this case, it does have two local extreme points. So right there, there's a local extreme point, and right about there, another local extreme point. In fact, if you found the derivative of this function, h prime of x, and set it equal to 0, you could solve for those exact x locations. Ends up that the local max over here, right there, that is, and you can verify this, the location approximately 0.92265, comma 1.38-ish, in fact 1.3849. Verified that ahead of time. You can verify that as well. The local min further to the right ends up being the location 2.07. Let's go a little further. 2.07735-ish, comma 0.6151. Now those are just some approximations, but you know, they're close enough. Let's just write approximately. Now, those are the local extrema for this function over this interval. But again, we are talking about the global extrema here. So we can notice that at the far left, that's clearly the smallest the function gets. Right there, right? So at that location, we're going to have our global min, and that is going to occur at the location, well, x is got to be the left-hand endpoint there, 0.25, and if you were to plug 0.25 into this function and figure out what it is approximately 0.297. So approximately. And our global min value, therefore, is at least approximately 0.297 here. The right-hand endpoint doesn't play much of a role in this situation because that point is not a local extreme point and it's not an absolute extreme point either. In fact, at the very first local extreme point, right up here, that is our global max location as well. So in fact, the 1.3849 number approximately, that's our global max value for this particular situation. And another thing to note, a function which is continuous over a closed interval, in this case, had one of its global extreme values occur at an endpoint, the global min here at the far left, and then it had its global max value occur at a local extreme point. Again, right at this location, it would follow that h prime of approximately 0.92265 is going to be equal to 0. So have a critical point there as well. So we've seen 3 examples now so far, and all of them involves, thus far, the function obtaining its global extrema either at an endpoint or a local extreme point as long as that function was nice and continuous and defined over a closed interval. One last one before we state the extreme value theorem, and that is this function right here, k of x, which is 2 minus the absolute value of x minus 1.5. And again, we're going to restrict it over a closed interval, in this case 0.35 to 2. We look at the graph, we can see at the left-hand endpoint again, there's a global min. So global min value at the location when x is 0.35, and if you plug that into the function, the output ends up being 0.85. So the global min value is equal to 0.85 here. That's the lowest the function gets over the interval. The highest the function gets over the interval is right there at that point, right? That's our global max location. Global max at the ordered pair. Well, notice that is when x is equal to 1.5, and 1.5 inputted into the function k here gives an output of 2. So the global max value here is going to be equal to 2. Now, unlike some of the other ones we've seen, this location where the global max occurs at x is 1.5, the derivative is not defined there. However, it is a local max location. And in fact, g prime of 1.5 is undefined, right? It's that corner spot. However, x is equal to 1.5 is a critical point of type 2 in this situation. So once again, we see a function that is nice and continuous over a closed interval, always obtaining both its absolute maximum and absolute minimum values. And again, it occurs at either an endpoint on the interval or at a local extreme point on the interval. So you might guess what the extreme value theorem is going to tell us. And here's exactly what it tells us, the extreme value theorem here. Let's suppose that you have a function, and, go figure, it is continuous over a closed interval, let's say a to b. Then, part of this theorem is guaranteeing existence, and that is that the function f must obtain its absolute maximum and its absolute minimum values on that interval. What it says is every continuous function over a closed interval obtains both its absolute max and absolute minimum values over the closed interval. Moreover, these absolute extrema, the max and mins, are going to occur either at x is a or x is b, so those are at the endpoints like we've seen in the previous examples, or we should say, a critical point location. So we saw that through 4 different examples, a variety of different situations for which this occurred. Now, this is clearly not a proof of the theorem, but it's supposed to help us understand the theorem. It can be proven. It's an established theorem. The takeaway is you have a continuous function over a closed interval, and we're asked to find the global extrema for the function. We evaluate that function at its endpoints, figure out what those are. We also find the critical points, figure out what the value of the function is there. And when doing so, we will come up with the biggest and smallest values of the function, the absolute extrema, over the closed interval of concern. Let's go take a look at a couple of examples here to wrap up this video, in which we aren't given the graphs, but rather we're given some functions, the formulas. Let's go and find, says the absolute, let's find, find the absolute extrema for each of the following functions on the specified intervals. So here's one function, okay? One such function, this polynomial function here, f of x, is the function 2x cubed minus 9x squared plus 12x plus 1 for values of x 0 to 3. Now notice, This function is a polynomial function, so it's continuous for all real numbers. It is continuous on the interval 0 to 3. Check. We also have a closed interval, 0 to 3. So the EVT, the extreme value theorem, guarantees that this function is going to obtain its global max and min values over this interval, and they're going to occur at either at the endpoints or at the critical numbers that happen to occur within the interval. Since we're going to have to find the critical points, let's go ahead and just differentiate this function first of all. F prime of x here is a 6x squared minus an 18x plus a 12. And since we're going to figure out where this equals 0, let's go ahead and factor this. That's a 6 times an x squared minus a 3x plus a 2. And even furthermore, this is 6 times an x minus a 2 times an x minus a 1. And because this function is a polynomial, it's nice and smooth, and hence the derivative is never undefined. In fact, the function's derivative here is 0 if the values of x is 2 or the value of x is 1. So these are our critical points of this function. And notice that, it's important, both x is equal to 2 is part of this interval, and x is equal to 1 also belongs to this interval. So it's possible that when you go and differentiate a function and find its critical points, those values of x might not be in the interval of concern. So you want to verify that just to make sure we're looking at the correct locations. So we got 4 points to evaluate. The goal is to find the absolute extrema for this function on this interval, and they're either going to occur at one of these critical points or at the endpoints according to, of course, the extreme value theorem that we just stated. So we'll just go through these. At x is 0. All right, let's check out what's going on. The value of the function at 0, pretty self-evident, is just equal to 1. Okay, that's at one of the endpoints. Let's just go numerically in order. X is 1, plug it in. What is the value of the function at 1? Well, that's going to be a 2 minus a 9 plus a 12 plus a 1, which is a negative 7 plus a 13, which is a 6. So that's at that first critical point, if you will. At x is 2, plug it in. F of 2, that's a 2 times an 8, just cubing the 2, minus a 9 times a 4, plus a 12 times a 2 plus a 1, doing some arithmetic since I don't have my calculator handy on me right now. 16 minus 36 plus 24 plus a 1, which is a negative 20 plus a 25, so that's equal to 5. So far, we got output values of 1, 6, and 5. And the last thing to do is check the right-hand endpoint, which is at x is equal to 3. Plug that into the function. F of 3, what is it? That's a 2 times a 27 minus a 9 times a 9 plus a 12 times a 3 plus a 1. Just multiplying this out, we get a 54 minus an 81 plus a 36 plus a 1. And what's that? That's a negative 27 plus a 37, which gives us a 10. What's the conclusion? The conclusion is the absolute max value of this function of f, right, is going to be equal to 10 at the location of x is 3. So that's at that right-hand endpoint. Moreover, the absolute min value of this function, f, is going to be equal to 1, and that occurs at the left-hand endpoint. So the critical points end up not being absolute extrema here, but that's okay. They could have been. And of course, this is over the interval of x's from 0 to 3. And so that's an example of using the extreme value theorem. Continuous function over a closed interval, we can find those absolute extrema by evaluating the function at its endpoints and also evaluating the function at its critical points within the interval. And whatever the smallest is, that's going to be our absolute min. whatever the biggest is, that's going to be our absolute max. Let's do one more before we wrap up the video. Here's another function, g of x. In this case, the natural log of x squared plus x plus 1 over the interval x belonging to closed interval -1 to 1. Now, take note, x squared plus x plus 1, that is strictly positive. And so we don't have to worry about this function being undefined, right? So right here, x squared plus x plus 1 is positive, and hence this function is always defined, and therefore it's always continuous because it's not a piecewise function, it's a composite function of elementary functions. So we got a continuous function again over a closed interval, and we know that the extreme value theorem applies in this situation. So let's go ahead and differentiate it to find any critical points there might be. G prime of x here, going to be chain rule, derivative of the inner function, that is a 2x plus a 1, divided by that inner function, x squared plus x plus 1. Now, again, the denominator is never 0, and so I don't have to worry about this thing being undefined for its derivative. And so the only critical point we're going to get is when this function is equal to 0, and that is when x is equal to -1/2. So there's our critical point of type 1, and notice that -1/2 belongs to the closed interval for which we are concerned. Now we go and evaluate. All right, g of -1. What is it? Our left-hand endpoint. That's the natural log of 1 minus 1 plus 1, which is the natural log of 1, which is 0. Going in order, go to our critical point here. G of -1/2, that's the natural log of 1/4 minus 1/2 plus 1, which is the same thing as the natural log of 3/4. And if you press a button to find out numerically what this is, it's approximately -0.2877. Finally, evaluate this function at the right-hand endpoint. G evaluated at 1, we get the natural log of 1 plus 1 plus 1, which is the natural log of 3. And button pressing tells us that the natural log of 3 is approximately 1.0986. So we can make some conclusions now. The global or absolute max value of this function g is going to be equal to, well, at least approximately 1.0986, or if you will, the natural log of 3 at the location of the right-hand endpoint, x is equal to 1, and furthermore, the global min value of this function, g, is going to be equal to the smallest out of all of these, which is the natural log of 3/4, or approximately -0.2877, and that occurs at x is equal to -1/2. And of course, this is over the interval of x's from -1 to 1. And so in this case, one of the global extrema was at an endpoint, that being our global max at x is equal to 1, the right-hand endpoint, and the other global extreme value, the global min of the function, actually occurred at the critical point here. And so that's it. I mean, we walked through some graphs, we investigated, we came up with the extreme value theorem, we looked at a couple more of examples, and so this isn't the end of the conversation about extrema. However, we're making progress here. And so the next thing that we'd like to do is, can we use our derivatives to go and classify local mins and maxes, and then kind of piece everything together? Find global max and mins and local max and mins of really any function there is. So that's it for the video. Hopefully it helped. And until the next video, it's Math and Beats. Later.